Yeah, I usually.
That's more and more official, Alexei.
Yes. All right, welcome back, everybody. We have clear asymmetry in the room here.
Cheers.
So we are getting back to the specifics of the facility that's going to be built in Taiwan. And Ernst Sichtermann is going to talk about tracking today. Floor is yours.
Oh, thank you very much, Alexei. And yeah, hello, everyone. Just out of curiosity, who here identifies as a theoretical physicist? Okay, so that's about 50–60%. And then maybe the other question is, who identifies as an experimental physicist? Okay, so that's maybe 30%.
Yeah,
Then maybe the next question is, who has a broken arm? Okay, so look, first off, it's really a pleasure to be here. I'm first of all very sorry that for me at least, this school ended up coinciding with a review that was scheduled later than the school. And that's not something you can turn down. So that's why I've been so lame in being here over the past few days, in particular. So I'll do my best to try and make up for it. And I think we should, no matter what you think about EIC, right, whether you're an experimentalist or whether you're a theorist or someone with a broken arm, we are pretty much in a really unique situation, actually. It's facilities and capabilities of this kind, they are far and few in between. So, look, you can hear several of our colleagues who will say that, oh, well, this turns on after my expiration date. Now, let's hope that that is absolutely not the case. I mean, and surely, look, this is the first facility you will see come online, I think, at a moment when it actually matters in career development and such. I hope that in the interim, enough enthusiasm can be built and kept so that this actually turns into a fantastic success. And furthermore, I think you will be the folks that do this with the next generation. So get those brain juices flowing on all sides, right? So tracking, as said, I'm Ernst. Just interrupt as you see fit. In the end, as with these type of lectures, first off, as said, I really appreciate being here. Thank you, Fred. Thank you, Alexei, for the kind invitation. Just a joy to do this sort of thing. And then, of course, if you have a topic like tracking or essentially any other topic that is covered in the school, you're basically standing on the work done by many, many, many people before you. That's not an excuse, but I'll freely borrow, and mistakes, of course, are my own in that borrowing, right? So now, if you say like, look, this is 5 minutes after lunch, I'm starting to feel sleepy, then please at least stay awake for this slide still. Okay, what I try to do here is put in a few references, and maybe I try to briefly walk through why I put these references here. So first off, irrespective if you're a broken arm person or not, the particle data group, passage of matter, particles through matter. There's absolutely nothing that you take away from this school on the experimental side, except reading that article and understanding it. That's success. It's a good review. It explains nearly everything there is to know, that you need to know about indeed the passage of particles through matter, what happens in terms of, say, ionization, what happens in terms of radiation. So in other words, how much energy you're transferring to that material that you might turn into signal you can actually detect. So the second reference that is in here is, well, it used to be Bloom and Rolandi. In the first edition, it's now Bloom, Riegler, and Rolandi, particle detection with drift chambers. Now you may say drift chambers, gosh, I mean, those were invented before I was born. That's correct. I think it's also in my case correct. Still, nevertheless, this is an excellent book. If you can get your hands on it through a library or well, even online, you will be able to find it. There are 2 chapters in there that actually walk in a very systematic way through, let's say, the generation of signal and measurement uncertainties and what sort of considerations you need to think of when people mention fancy words like calibrations. In addition to that, I think it's quite pedagogical if you want, let's say, an introduction, but more than an introduction, that has a decent notation and such to tracking in particular ordinary spectrometers. So the 2 chapters there are certainly worthwhile. The rest is worthwhile too, by the way. Okay, but the handful, right? Then the yellow report, I'm sure that it has come up before. So that's the obligatory quote here. Look, many people will at one point or another in their lives use these sort of pocket formulas, right? That have things in them like square roots of 1 over n plus 4 or n plus 5. And then you have these big debates with your friends. Well, is it 4? Is it 5? You never figure it out. Just go back to the original article, read it, and you will actually understand that it's 5. Okay? So, of course, there's an update to that. There are many, let's say, more modern tracking articles. They tend to become mathematical, I would say. So that's a bit of an acquired taste. Nevertheless, I think this one is accessible. So go for it. And then, look, even if you don't care about tracking in the end, I actually think that Paul Avery on his website has a very nice set of articles about the theory of fitting. That's worthwhile for many, many reasons. So if you wondered about things like, oh, how does a kinematically constrained fit work? How does a beamline constraint work in track fitting? Why do the uncertainties improve? What are the consequences? It's a good read. Lastly, if you're a computational physicist, so the ones that will have broken arms if you don't pay attention to ergonomics, then and you're into tracking, there was a recent workshop on ACTS, which is currently the experiment used software and partially co-developed, I would say even. Of course, there are many, many more, right? That was not the point. Now, tracking can mean many things to many people, and we need some sort of classification as to what we are talking about. So I made one here. So tracking and vertexing as a measurement is intended to be minimally invasive. It's usually based on ionization. So ionization energy transfer, right? Basically, you knock an electron off an ion or an atom, it becomes an ion, and then typically it's the electron that propagates faster in some form of field, and you then amplify it in another field, and in the end are able to detect this as an electrical signal. The main point is that the energy transfer from the original particle in that needs to be relatively small. So for particle identification, there are multiple mechanisms. Of course, for tracking, there are multiple mechanisms as well. But those mechanisms do not necessarily give you information to what the particle actually was. So for particle identification, that could be indeed also the ionization energy transfer by itself, if you carefully detect it, indeed, and you observe it. Time of flight of particles, right? So even relativistic particles, they do not move at the speed of light. If you measure their energy and momentum, you get insight into their beta, and with that you can get access to their mass. That's a way of indeed getting to their identity in the end. Cherenkov radiation, so basically a particle that is too quick for the surrounding medium, and with that it typically emits this wonderfully blue light. On occasion you get to see. Transition radiation is yet another phenomenon of radiation as a particle transitions surfaces in the end. So multiple ways for particle identification. Thomas Ulrich gave an excellent lecture last week, if I remember correctly. I looked at the slides. You can find everything you want to know there where it pertains to DIC. Calorimetry, of course, featured this morning by Barak. There I would say this is a very different category of measurement. The trick really is about capturing the particle, capturing all of its energy, and then it is essentially gone for further detection. Of course, by capturing the energy, you try to translate that again to an electrical signal, typically, perhaps through an optical signal first. Now, there are multiple forms of interactions to this. There again, you can make a classification between electromagnetic and hadronic. Now, if you look at this, of course, it's not this rigid, right? I mean, I said here that this ionization energy transfer for tracking, it needs to be small. Well, how do you control that? If you cannot limit the amount of material in your detector, then it is what it is. Who am I to say that it's small, right? It's not a calorimeter typically, but there's a transition region. If you take something like a time projection chamber, who knows what a time projection chamber is, by the way, as a detector? You do? Why don't you walk up here and just explain? Okay, we'll get to it then. Don't be shy, right? I mean, but thanks for mentioning it, because now you can keep me honest once we're a few slides further, if that's okay. Okay, so time projection chamber, in the end, what that does is it measures both a track curvature, and depending on gases in your configuration, it can also measure the energy loss. With that, you can actually get access to this beta, and with that, you can identify low energetic particles typically. Okay, time of flight systems, likewise, they can be carefully segmented. In that case, you gain tracking information out of them in addition to the time difference from the path that is traversed. So it's again a mix. Of course, if you think about a vertex tracker, what it does is it determines vertices as well as displaced vertices. So vertices from decay. Decay length is again a particle property. So with that, it's actually a particle identification system as well. Now for the evening, right? I mean, so after we've all digested this lunch and, well, we've eaten dinner, there are candies, as I understand it. We get all sugared up again. We have all the energy to go at this. Let's, for EIC purposes, you've seen this tiny yellow report right up. It's only 844 pages or so. You can look up what the calorimeter as well as the tracking requirements are, what the resolutions are. Figure out where does the detector actually rely on its energy measurement with the calorimeter, in what energy regime that is, and in what energy regime you rely on momentum measurement with your tracking detectors. Where is that crossover? Anyone have conjecture how that works? As in, at high energies, would it be better to use a calorimeter to measure energy, or would it be better to use a tracking device to measure momentum?
Maybe it's better a tracking device, because at high energy, we are not sure that the particle release all its energy inside the calorimeter.
Yes, that's so the leakage out of a calorimeter can cause biases, right? That's essentially the argument you're making.
But I thought that if you have if I have a higher momentum and I want to see the bending, I won't get enough hits if I'm going too fast, no? Like I won't really be able to, it'll look like a straight track.
Exactly. I think you get the same number of hits in the end, right?
Uh-huh.
Because that is how much you traverse in
Yeah,
the
sorry.
end. But the curvature of the track becomes less and less. And you're right by implying that it's easier to measure a large curvature than it is to measure a small one. And that's clearly an effect that, well, the radius of curvature increases as the momentum increases. With that, the track becomes more and more straight. So in other words, for higher energies, your track measurement becomes more and more difficult. And in your case, with the calorimeter, right, you start from a point where you're fully contained. The shower becomes bigger in the calorimeter up to a certain point, and then you start to escape from it, right? So figure it out in the evening. Okay, you here have two counter running effects, right? But once you start to figure in biases, the game can change. Okay, that's for the evening, right? So quick summary here about, in the end, how do you detect particles? I think and hope that this is relatively well known, at least among the experimental colleagues here. Among the theory colleagues, it's never too soon. Okay, I mean, you have all these wonderful interactions this week, make use of it. We are mutually dependent, so use it. You can read faster than I do, but let's focus for, then I can speak, that is. Let's focus for a second on this very last column here in the end. So let's have a look here what where tracking actually plays a role. Right, so in the case of neutrinos, missing energy. Well, might be measured over missing momentum in the end. So perhaps an anti-detection, if you wish, involving tracking. Some level. Electrons, obvious, relies on the track, relies on the shower. So that's a combination of tracking and calorimetry typically. Ions, penetrating track. That must have to do with tracking in the end, right? Stepping it down further. Ions, protons and kaons, track, and the hadronic shower. So this is certainly one of those where, well, in the evening, you'll figure out where this transfer is in terms of energy. Okay, but again, tracking plays a part. Photons, that's a mixed bag. Okay, photons can, of course, interact electromagnetically. Now, if they do so, they can pair produce. And actually the pairs you might be able to observe also in a tracking device. So it could be. Traditionally, this is the realm for calorimeters though. Then for a joke, okay. Does anyone know what about the best calibration devices for a time projection chamber?
Laser?
Right, and a laser produces photons, right?
Yeah.
Okay. For those who don't give up early in the evening, figure out how that works in a time projection chamber. Okay, it's actually quite intriguing how that works. Okay, neutrons, yeah, okay, K long, likewise, that's calorimeter stuff. Weak decays, secondary vertices, minorly displaced. Does anyone know what the scale is on this sort of thing? I mean, is displacement of this decay vertex, is that centimeter? Is it a millimeter? Kilometer?
Centimeters. No, it's millimeters because Star had a heavy flavor. It has to be pretty close.
Is it smaller than centimeters, maybe?
I think so, because it's really easy to mess up B and C for jets.
So we have an expert in the room. Do you want to comment?
Microns.
Is it?
Micrometer, like
I
1 to
I
100
said less than
micrometers.
centimeter. There's a lot of range.
Okay, then in the rebounds, how is that for hyperons? So lambda particles.
3 centimeters.
And when they get boosted, it's significantly more. There's indeed a difference in the end. Okay, and then look, prompt decays, typically invariant mass. Of course, there you measure a thing like an opening angle as well as 2 energies. So it's again a tracking problem, right? In other words, tracking is everywhere. Essentially. Okay, now what I want to do is show you a number of detectors that are sort of old, but I think you should be aware of them. Many ways of looking at them. At the time, I think it's fair to say they were state of the art. By looking at them, I think you will see eventually commonalities, differences, and also get a sense for what would work and what would not work for an EIC or any other facility for that matter. So what you see here is, I'm sure that you've seen the figure on the right more than once, right? I mean, in the end, that's what gave us deep inelastic scattering. It's often then overlooked is the instrument that was necessary for it, as well as the facility. So what you see here is a fixed target experiment with a beam coming in from this side, and then two spectrometers, a lower energy and a higher energy, that actually are able to detect scattered charged particles. Does anyone have any idea why that shape is like that or not? Yeah, it's a magnetic field. So also a question for the evening. Why is it a magnetic field for these energies as opposed to an electrostatic field? In the end, I can bend charges and currents both in a magnetic field and in an electrostatic field, right? So maybe a good question for the evening as well. Okay, moving on. Another type of spectrometer. This thing looks straight as can be, but what you actually have is a beamline here with a magnet that bends in the plane, and then it's what you see here is a number of larger wire chambers followed by what is called a muon arm. So essentially a big ball with behind it hodoscopes. This actually is the start of the European muon collaboration experiment and spectrometer that is currently or was currently slight decommissioning there as well at this point. The compass experiment at CERN. So many generations of upgrades, if you wish, got us there. Key point here is that it's a muon beam that's not applicable to the current version of the EIC, of course. On the other hand, the muon detection techniques might be. Okay, what do you have here? The time projection chamber, right? The star one, which is one of the early generation ones of it. So what you see here is a solenoidal magnetic field. Inside of it, this time projection chamber. Then maybe a quick word on how it works. Typically, what you have is, of course, the magnetic field that is along the beamline, right? So this is the beamline. Then inside this TPC at the midplane, you typically have a high electrostatic potential that in the end causes particles to drift to the end, where the drift electrons then typically are amplified by showering over a very short distance so that they can be picked up as an electric signal. That happens inside a gas. The drift time for that is relatively slow at the level of 40 microseconds in the case of star, but think tens of microseconds basically for any TPC of this sort of scale. That's of course slow compared to some of our nanosecond timelines we deal with for photomultipliers, or picosecond timescales for time of flight techniques in the end. Now here you see another detector, the CMS detector. What you see on the outside actually is a vast muon arm. And on the inside you see a silicon tracker in the end. What is the difference between the star detector and the CMS detector? What are differences? What are commonalities? Anyone want to comment?
We have a magnetic field. They both have a magnetic field. But this one, they both have well, I want to be careful. I know this one has like a more, I think it has a hadronic calorimeter. We have a forward, but we don't really have the full coverage at start. We have a little bit of an EM calorimeter. I think they do too. They measure full jets. Higher energy. We don't have silicon. They do.
I think so. First off, thanks. For tracking purposes, the key difference that I would see is actually the magnetic field. It's 0.5 Tesla versus 4 Tesla. It's astounding that there is a magnet of this size with a field of 4 Tesla. That's not something you can do today in practice. And so that I think is a huge difference. Other than that, for our theory-minded colleagues, think a bit about the phase space. Okay, so what does it mean to have an eta coverage of ±1 at RIC versus, let's say, an eta coverage of, well, it's more than that, but ±1 at the LHC in terms of phase space. Now for something entirely different, what you see here is the IceCube telescope. Okay, we had this talk that neutrinos, you can't detect them. And well, hold my beer is sort of the response from our astrophysics or astroparticle physics colleagues. They have done is an instrument that speaks to the imagination in many ways. It's at the South Pole. It's a kilometer below the ice surface. It's equipped with optical detection DOMs, so digital optical modules, they call them, on strings. And actually what you see here is an event display where a neutrino interacted inside of the detector under production of a muon that is then detected as both an energy deposit, as in the energy that muon deposits, as well as a time sequence in the end. And that is what allows the reconstruction. There are different signatures. This is a fantastic testing ground for event reconstruction, I would say. If you are into deep problems with that, go for a detector like this. You can't beat it. Okay, now look, EIC detectors, right? We've seen all detectors that don't work at the EIC. There have been detectors at the earlier EIC era that did work. So here they are. They look remarkably similar. They look remarkably similar in a way to STAR and to CMS. Magnetic fields, 1.2 to 1.4 Tesla. So, okay, why would that be? What does it gain? Right, and then there are some complementary strengths that are often touted in current analysis as limiting systematics. That's wonderful. You can ask the question, is that fortuitous, so accidental, or is that by design? And well, for those of us who start sort of the evening at 11 and then end it a couple of weeks later, an evening question could be, what should a second EIC detector look like? I think it's a serious open question within the community. Okay, look, this we've seen, the onion, right? I mean, it's clear that you do not put calorimeters as your first layer of detection because it's a destructive measurement. It's the other way around. You start typically with tracking, then PID, and you build your way out. So what should that EIC detector look like? Okay, well, theory view. It's obvious what you need to do. Okay, I mean, we just want to have the form momenta, all particles. We want to know what particles they are. Uncertainties, yeah, okay. I mean, that is in some textbooks or so. We don't want that at the EIC, right? So now ask your experiment friends, and they will come up with a comment like, "Oh gosh, there are trade-offs. I need to guide in cables. I need to guide them out. There are gaps everywhere. How do I deal with it?" So you get a very, very long list. In the end, practical detectors are trade-offs, always. Okay, that's also the reason why a second detector can truly be complementary if it's designed to that. In the end. Now, you can ask the question, what does tracking do here? Right, so, okay, this is the long version. So let's take a step back, right, just ask about key processes. Again, so if you look at this, of course, inclusive scattering, semi-inclusive scattering, exclusive scattering, diffraction, maybe. In the end, in all of that, of course, the scattered electron really matters. Okay, compared to prior measurements at the EIC, there's certainly very vast phase space to be explored in semi-inclusive deep inelastic scattering. Thanks to particle identification in the detector, you can make leaps and bounds in understanding, for example, on, let's say, evolution in nuclei. I would argue. I'm happy to debate that. Likewise, having the luminosities at the EIC means that you become sensitive to exclusive processes. Okay, so certainly what this all has in common, most of it has in common, is the scattered electron. That's a must-do. It's necessary, but it's not sufficient. Certainly, you would want to detect the scattered proton here as well, for example. Okay, this figure I think you've seen.
I just have a quick question. For the previous one, for the one at the top with the neutrino, the idea is that you would measure all of the whatever was
Yes.
the remnants and then work backwards. Okay.
Yeah, it's a missing
Okay. Yeah.
missing energy and missing momentum argument, and there have been initial studies on that, which I can point you to, though not in real time.
Okay. Thank you.
Oh, the other button, right? So this figure you've seen, right? I mean, let's not spend too much time on it. What do you have, right? I mean, you have this x and q squared plane. And quite often that's sort of where it starts and stops, right? As an experimentalist, of course, we need to ask the question, well, so suppose I have this electron measurement. How do I actually determine x and q squared? So relations are given here. In the end, what you also see is that if you're interested in this region, let's call it photo production, that your scattered electron actually all goes in the forward direction and that the energies are pretty high in the end. Okay, so that's a direct experimental consideration. Very forward detection is needed for those processes. Okay, stepping through it, you can go to somewhat higher x. What do you see? It opens up a little bit in angle. Step again further, right? I mean, still, so rapidities of, say, 3 in absolute sense. That's something like a few degrees away from the beam pipe. In the end, step it further to, let's say, mid-x and higher q squared. It opens up a little bit further to pseudo rapidity of about 1.5. Well, that will be angles at the level of, say, 160 degrees or so in the end. And then the largest x and q squared, in the end, you see that actually only half of the detector is roughly used for all the electron measurements. Right? So why are you building this Coke can instrument with a forward and backward region if all you're interested in is the electron? Okay, there are at least 2 reasons for that. One of them is that actually this reconstruction doesn't work very well as y becomes smaller and smaller. So in other words, it does not work very well as you go more and more in this direction of the plane. Okay, you need an alternative to that. That has been worked out. You see it over here. There are at least 4 methods for it. Also more modern versions of this, by the way, including neural network reconstructions. So what do you see in the end, right? I mean, of course, we have the ordinary electron method that we all know. X is boring. It's always determined from 2 other invariants, but you see clear differences in how both y and q squared are reconstructed. Okay, in this case, it's of course all from the electron. If you now look, for example, over here, you see that there's a sigma term, which is purely a hadronic term, as you see up there. There's a t squared term, which again is a hadronic term. And there's a subtraction there. So what is this? It's a hadron method in the end. Likewise, and I'm not going through all of it, you have something that actually measures double angles, but rather uses the angular measurements as opposed to energy measurements where that is possible to reconstruct the kinematics. The experimental advantage of that is that you do not need an absolute energy calibration to some extent, of course. Now, where does that work? You see that illustrated over here, and actually you see very nice complementarity for different regions between these methods in the end. So the other argument, which I alluded to already, why you absolutely need this full detector and full instrument equipped with tracking is the semi-inclusive DIS set of measurements that covers quite a lot. So what do you see here, right? I mean, this is all still calculable on a piece of paper. The electron side, the hadron side, and then look at how lines of constant angle or constant pseudo rapidity work. In the case of the hadron, you see that they sort of build up along this diagonal. In the case of the electron, you see that they build up vertically. That means that your hadrons and your electrons are actually divergent, if you wish, in their direction in the end. And that is what drives the full coverage that you need. You clearly see where in the case of the electron, you run out of steam indeed on or about, say, 0. In the case of the hadron, that's absolutely not the case. You see here, for example, here, this is this line of pseudo rapidity of 1 in the end. Okay, and that is smack in the middle of the DIS region. Okay, now what should the detector look like? Like this. It needs to be compact. It needs to be well integrated with the interaction region in the end, and you need forward and backward detectors that are very, very forward and very, very backward. So in other words, it's a huge enterprise in the end, the full detector. Something like 80 meters long or so, where of course the distance is determined by relatively small detectors here and relatively small detectors there, What sits in between is really the facility in the end. So central detector, that will of course be the focus of what follows. What should that detector look like? Now, for sure, it needs to be compact. That's the way you get luminosity. So again, referring to Thomas's talk, building it up at this point. So in yellow here, color coding is a little bit different than on the previous slide. You see the tracking detectors, so on the inside of the instrument, building outwards, PID that surrounds it in various forms. Again, look at Thomas's talk, why this is so different in terms of geometry that you need. Calorimetry on the outside, and typically the dominant part of the instrument in the end, in terms of weight, in terms of dimensions. So tracking, that's of course the interest I have here for the purposes of today's talk, at least. So the core functions of the tracking detector is precision tracking. We can talk about what that really means, as well as vertexing, right? We did want to detect these or the 10 micrometer displaced vertices in the end. So we'll see what you need for that. Okay, and then track pointing to the PID subsystems, as well as track length for time of flight measurements. Does anyone have an idea offhand if you have, let's say, a time of flight system that has a resolution of something like 25 picoseconds, how accurately you need to measure your track length? I'll not wait too long, but eventually it will be evening. Okay, just calculate that. It's interesting. Just do that for yourself. Okay, and turn that around as well. What is it worth to, in an EIC experiment, to strive to improve time of flight resolution to 10 picoseconds in the end? Is that worth, say, half a decade of your life? Figure it out for yourself, okay? Don't listen to your supervisor, they will say yes, but it's not their life, right? So figure this sort of thing out for yourself. I'm actually dead serious about that. And then, pointing to the calorimeter subsystems. So now, 2 words about technology. Again, Thomas's talk covered much of technology. So to get to these 10 micrometer-ish displaced vertices, you need instruments that have similar resolutions in the end. The technology of choice for that, and the only technology practical at this point, is silicon. Of course, if you have indeed resolutions of this level, you have energies that are relatively modest. It's very easy to destroy that resolution with multiple scattering contributions. And we'll get to that. You can calculate this yourself. So not only does this need to be silicon, but it needs to be a specific kind of silicon, namely silicon that can be thinned without losing its active properties. So what that means is that this epitaxial layer, which is the sensitive layer in the silicon, actually can be very thin. You see it here at the level of 25 micrometers. Okay, and then what happens in that epitaxial layer, that's in essence the same as what happens in a drift chamber. A particle comes through over here, it ionizes, it breaks free electrons out of it. Those electrons are drifted towards the diodes. And then depending on the type of silicon, there are fancy words with that, but this, the mechanism is all the same always. Okay, so then what is needed to achieve these very thin layers of silicon is, of course, that you don't ruin it with a humongous readout structure on top. So instead, you strive to integrate that. That has succeeded, has been used in experiment at this point. First was STAR, second was S-Phoenix, together with ALICE. Say those are the same detectors in the development. For that effort was led by ALICE. So this works. Point resolutions you can achieve are at the level of 6 micrometers. Now, point resolution on a small chip device is not the same as a system resolution. Okay, don't worry about that if you want to. I certainly do. Then other technology, which is for the tracking detectors that are somewhat further out, so larger areas to be covered. Resolutions don't need to be that precise. Cost considerations come in very, very different ways. The choice of the EIC project detector is at the moment 2 variants of what are called micro-pattern gas detectors. These are, I would say, innovations on top of drift chambers. So what are the innovations? If you wish, the innovations are in the readout planes. So where for drift chambers, this is always about single wires that you then can cross and such. That's not the case for a structure like this. The other part is miniaturization of these devices. So the drift gaps are now at the level of millimeters quite often. And then the amplification is done with, could be a mesh, it could be indeed a bell. In the end, a readout can be directly coupled or indirectly coupled, so capacitively coupled. There's nothing simple about this. This sort of development takes a decade or two compared to drift chambers in the end. Okay, tracking and vertexing then, right? So what do we typically need for tracking in the end? You need a form of coordinate measurement. That's what starts it all, the 6 micrometers in the end. You need a track model if you want to get to tracking. Then you need to find those tracks from hit positions in the end, and you need to fit them in one form or the other. For vertexing, sort of the same story. Okay, I mean, it's indeed about finding the vertices, so reconstructing them, fitting them, and then you can indeed worry about the secondary vertexing. So this sounds very simple, right? It isn't, actually. So analytical solutions exist. Certainly, we'll see one of them. Maybe 1.5. But that's select cases. I don't think that everything has been analytically solved. As soon as you insert, let's say, an energy loss or a friction term anywhere, it all of a sudden becomes considerably more complex. If you want to get an overview of a large slew, I would say, so more of an encyclopedic write-up than, let's say, a pedagogical one, this is a very good one. It's also fairly recent. So coordinate measurement. What about square root of 12? Who knows about square root of 12 for resolutions here? No one? Really?
It was like integration of x dx from -1/2 to +1/2. Like
Yeah, that's
from there,
exactly right.
Yeah.
That's
There
exactly
we
right.
get root 12.
So let me see and then keep me honest, right? Tell me whether I just capture what you said, but I think you're spot on here, right? So what defines a standard deviation in the end, right? I mean, that is always something like an, let's say, an average minus a measurement or the other way around, square it and sum it, right? And then take a square root in the end. So it's something of this sort. Now imagine that I have a binary measurement that I make over here in the end. Okay, that's the location of my pixel. Let's say then it has a spatial extent that is something like this. Okay, I'm just going to be lazy in the end, right? I mean, what I'm going to say is that this is my origin. Let's call it like that. Then if this is the pixel size in the end, this instrument, right? So some pitch of some sort, I could call this half x, and I could call this minus half x. Then if I need to evaluate something like this for an illumination that occurs on a scale that is just much, much larger than the pixel size, it's essentially flat. All I need to do at this point is integrate from minus half x to half x, what is it, x squared dx. Okay, there you end up with your 1/12. And I need to take the square root. And it becomes an x to the third here, the 1/3 in front of it, and you have this half over there and over there. Right? And that gives you the additional factor 4 in all of it. All there is to it. Okay, so we know now about this square root of 12, right? We don't need to guess anymore. Is it square root of 12, 11, 13? We know the assumptions. Thank you. Clustering, right? How can you improve on that? Not everything is a binary hit in the end. So, look, you could have a situation where you have 2 measurements in the end. So one measurement here, one measurement here. For whatever reason, I have a pulse height like this here and a pulse height like that there. Those are two measurements. They add information. I could weight by these pulse heights and get better precision points in the end. So it's again one of those where your supervisor may suggest that you do that. And again, I would suggest that you Monte Carlo that first. Because this typically comes about when people are a little bit disappointed with the actual outcomes and they want to have them better. That's not always possible, okay, or it's not always worthwhile. You can spend a lot of time on algorithmic improvements. This type of improvement totally doesn't help you if you're in a situation where multiple scattering dominates. Okay, so make the point to calculate that yourself, I would argue. Split signals or propagation time. So propagation time is exactly what happens in a time projection chamber, right? We have a track that goes through. It is in an electric field. Electrons are drifted to the side. They are picked up. You measure is T0 if you wish, and then you measure the arrival time. Or the difference of arrival times does the same thing in the end. By knowing the properties of that gas and keeping them constant and having them calibrated. In principle, you know this distance if you know the time. In practice, you also need to consider that by taking out these electrons, you've actually left behind a positively charged cloud, and with that, you've changed the local field, which does affect the drift. So time projections are beautiful devices. Calibrations of them are not simple. Laser systems are wonderful for that sort of purpose, by the way. Split signals, that's typically something where you needed a long wire of some sort, okay, typically to reduce cost at the end of the day or to be able to integrate, and then you instrument it from both sides. Signal comes in and then it propagates to both sides. If the lengths are different, you can do that with the time difference. Likewise, if there's some form of attenuation, you can measure the ratio of amplitudes and get information from this. Okay, so tricks to go beyond the square root of 12. That's all that comes down to. And then the track model. Well, the obvious one, straight line, right? I mean, that's one step above a constant. 2 steps above a constant would be a parabola. Helical, then it quickly becomes a little bit more involved, I think. What then often happens is like, oh, a helix, yeah, okay, that's a circle in its projection and a line in the other projection. We've all played this game at some point. Okay, I'm sure. Projections are tricky. Okay, have fun with it, memorize it, but be aware that if you do this in an actual experiment, you can have the same situations as you see here. Okay, now fundamentally, of course, the track model in the end is determined by equations of motions. Motion. In practice, you will have distortions, again, from, let's say, multiple scattering, from ionization energy, redistribution or loss, from hard scattering. You could even have some nuclear interactions, could be all sorts of things in the end. That's what makes this difficult in practice, besides tedious mathematically, quite often. So, track finding then, I would say it's intuitively clear when the hit densities are low. I mean, everybody can fit a line to 2 points. Okay, 3 points. When you see 3 points, it's usually clear whether you can fit a line to it. It's usually also quite clear if you sort of have some V-shaped thing or some ambiguity. So those are, of course, all relatively low hit densities, if you wish, or hit numbers. In practice, this is almost always a cookbook to keep it computationally efficient in the end. There are algorithms that are local, so they look for, let's say, track extrapolations, for example, or interpolations. And there are also global algorithms that consider every single hit and then try to fit it to a track effectively, make it fit a single track. We'll see an example of it. I think it's a good one. It's known as this Huff transformation. Not often used nowadays anymore, but it's remarkably elegant. That's why I want to show it. Track fitting, that's again quite clear if the problem is Gaussian, and beyond that it gets complex rapidly in the end. You worry much more about, let's say, biases, robustness of it. So indeed, biases in the case of calorimetry could, if you lose part of your energy, that just means that systematically you measure less than what you actually had. You can have this type of problem as well from, let's say, a misaligned tracking plane. Okay, it tells you that you're in a different place than where you actually are. It's bias as well. Okay, straight line fits, right? I mean, I guess who has not done a straight line fit in their life so far? Who has done a straight line fit in their life? The arms still work. Okay, then we don't need to do it on a blackboard. That's great, right? So I think then we can quickly get to some of the properties, right? So suppose I have these 5 points, right? Let's simplify it. All those 5 points have the same uncertainty to them. Furthermore, the distance between these measurements are just all equal. At what point are the slope and the intercept uncorrelated? Okay, I should have asked it differently, right? So everybody has done a linear fit. Who has actually propagated uncertainties in that linear fit? Who still has a working arm? Okay. Okay, this is a simple mathematical problem, but it actually really matters in the end. So I'll give you the answer. Think about it in the evening, and we can also just work it through. Okay, the slope of a linear fit pivots around its weighted average, which in this case is just the same as the geometrical average. I have 5 points, and this is the center, clearly, if they're equidistant. It's around the center, and it's in the center point where these quantities A and B. So if you write it as A at this center point, of course, and then you offset X to achieve that, right? So you shift this axis, or C in this case. That is where these measurements are truly independent. So you can work that through. Okay, you can work that through what it means in terms of uncertainties. In the end, you can work it through in terms of extrapolation uncertainties. Okay, to a point outside of your tracker. In the end, these are the answers you get. So here you have, again, one of those n+5 situations, right? Work it through once, you will know, and your friend will not ask you again and again, oh, what that n+4 or n+1, what was it? You just know at that point. So looking at such an equation, right? I mean, suppose I need to improve this as an experimentalist. How do I go about that? So I need to drive these numbers down. What is common to them in the end? I see a term sigma squared here, sigma squared there, which was this measurement uncertainty. So in other words, put more precise detectors in there. Kind of obvious, right? What else can you play with? Well, there's some n's in there, which are the number of measurements. On the other hand, if you look at that, right, I mean, there's sort of an n squared like term here, an n there, so that's a 1 over n. Likewise, you have something like that over here. So in other words, improving on uncertainties, not uncertainty squared, is actually significantly slower than improving on your actual measurement resolution. If you need to choose, you always pick measurement resolution over additional material. Simple as that. And it's just too slow. It introduces more material than you actually gain in terms of measurement precision. Another one you can really play with is this 1 over L squared term here. Right? What is it? It's the lever arm of that device. Long lever arm is almost always helpful. So these are things that you can easily take away from really fairly straightforward fitting exercises. Okay? And they are remarkably important and directly applicable to considerations in an experiment. Because this, what you see here, is of course a local approximation of a vertex fit in the end. Locally, tracks typically don't bend that much. these distances are relatively small. Of course, you need to quantify that and make perhaps corrections to it. This is exactly the problem you have for a vertex fit. What are, in practice, then difficulties that you will encounter? Well, typically you have such a pesky thing as a beam pipe sitting between your detector and your collision point still. So that introduces multiple scattering, slight complication, single plane. Okay, straight line fits, right? I mean, the EIC is not yet built. So at this point, one of the exciting things you can do is participate in test beam efforts that aim at developing new sensors. So typically, and you see here an actual example of it, this is an example that was used at Fermilab. So typically what you have is a device under study, it's called, sits in the middle, and then devices multiple on both sides. Okay, since we know everything about linear fits at this point, you know, in principle at least, how to align this entire system. You know how to determine the measurement resolution, right? And furthermore, from the correlation, if you reverse this, you can delineate actually what the measurement resolution is, as well as what the multiple scattering contribution is. You can get the separate answers, so you can get insight into the thickness of this device as well as its resolution, as in its point resolution. Happy to sit down with anyone this evening. Okay, just saying. Okay, half transform, I mentioned this, right? So again, these linear fits, that's not epic. We have a 1.7 Tesla magnetic field. Why are you bothering me with linear fits? Well, in many cases, it's actually possible to transform circles into straight lines. Yes, comment about projections. So there are fancy names for that. Okay, here you see a transformation that actually does that at the top. So these are curved tracks, right? I mean, it's a circle equation over there. In the end, in, of course, a specific coordinate system, but that's fine. You see all sort of curved tracks. Apply that transformation, what you end up with is straight tracks. Furthermore, you have this relation, which actually is the relation of a line. Okay, now go for a further way of looking at this. If you don't look at this as, let's say, a line with fixed points, but you turn it around, you make the line about the parameters of so the slope and the intercept, those are become your parameters, and your hit points become the fixed constants, and you have a parameter space in those intercepts and slopes. Now, slopes are ugly, they can become infinite. So typically you do that in some form of angle and amplitude transformation to keep it all a bit finite. Okay, so what often then happens is that you transform into, well, C and phi space. That's okay. If your hit points originated from the same track model, they should intersect in parameter space. I may not know what the parameter is for a single point, but in collection I do know. So I can plot for every single point what this parameter space is, and I can look for the densest areas, intersection problem. So that's behind a half transform. Computationally, this is of course somewhat expensive, because basically you need to consider every single hit. Okay, as compared to, let's say, an algorithm where you forward swim a track and you just don't look at this vast amount of hits. So that is also what I meant by a global look at tracks. This has been used in multiple experiments. Actually, UA1 is a very old example. Likewise, class 12 at JLab has used these type of tricks at one point or another. Not arguing that this is the best way of going about it. Just want to outline some pieces of creativity that have gone into this. Okay, look, we're almost in the home stretch at this point. So, motion in an electromagnetic field, right? That was his earlier question. Why is it always that if you open a textbook that you see motion in a magnetic field? And actually, if you look at the equation that you then often get, what does it truly mean, right? Relativistic particles. Well, the main point here is that that is the relativistic momentum. in the end. That's the one thing to keep in mind. This can be the lap time in the end. So of course you can think in terms of track length. Again, that's often denoted by S in the end, and that means that you can cast this into an equation like this. Okay, moving away from the circle projections. The circle projection is given here. This is a very good pocket formula to have in mind. Do a bit of math with it, right? So can we do that in real time actually? So let's say for magnetic field of 1.6 Tesla, right? Then for a momentum value of 3.1 GeV, what would be the radius? Is it meters, centimeters, kilometers? So who has read the recent release of the muon G-2 results, or who has seen it? Did you see a picture of the experiment? Oh. Mhm. Mhm. And what was roughly the size of that magnet? It's bigger than a person, right? Okay, we'll do the math. Okay. Look, that's why these pocket formulas help, right? 1.6 times 0.3, what we can do, it's about half, right? The momentum was about 3 GeV, 3 divided by half, that's about 6. So the radius of that experiment is about 6 meters. That's about correct. Of course, it was a precision experiment, right? So you don't get away with saying that the experiment was 6 meters in diameter, but yeah, it's close enough, okay? Okay, then maybe turning briefly to disks. This goes at fitting of curved tracks in the end, and it does so in projections, caveat on projections, right? So let's work through this relationship that we just saw, that the momentum, transverse momentum is 0.3 times magnetic field times the radius of the experiment. Okay, then if these tracks indeed curve, one way of getting at this momenta is by measuring this sagitta. You can write that out, what it is. This is a convenient set of variables, I would say. So the trick is really to just write this as half an angle as opposed to an angle. Simplifies the math, so that's also I can do it in the end, work that through. What you get is that this sagitta is at the level of the radius of curvature in that case, right? Phi squared, which is this angle that you have here, the full opening angle divided by 8. Now you can also compute what this phi is. You can see it over here, what it is effectively. That means that your momentum measurement in the end has a relation that goes as this delta S. Well, you can measure that divided by L squared. Increases with PT, you had commented before, and divides by the B field.
Question. Am I thinking, okay, I guess I was just surprised that it was pointing there instead of like going forward. Maybe I'm thinking about it naively. I mean, I've never done.
Yeah, so what you see here is the beam pipe opening of this disk, right? Magnetic fields. So it's either way. I mean, it's one choice that is made. It's a forward disk, and you look at projections of points in a sequence of disks. In the end, that projection looks like this, and then the origin, such a circle, does not coincide with the beam spot. It lives away from that, right? I mean, that's how you can create different phi angles, for example, that all originate from the beam point, but they all have different origins in the end. So that's. I hope that is helpful. Okay, here we have the notorious.
How do they take care about non-uniformity in the field?
Sorry, I didn't hear what you said acoustically. Could you repeat, please?
Take care of non-uniformity in magnetic field because field won't be uniform, right?
Yes. If you do not have a uniform field, then you have no other way than solving the full differential equation with the magnetic field in its coordinates. What you typically do in such a case is at least reduce the number of coordinates. Okay, so for example, you could know that your magnetic field falls off because of the coil length as you go further out in Z. That's typically a symmetric function and it's something that gradually falls off. And likewise, as you grow in the experiment, there are typically fall-offs. All of a sudden, it's not longer X, Y, Z that you need to solve, but it's just Z plus R squared or R. That's at least one reduction. But yes, you need to solve it at that point, often numerically. And there are very tricky instances like for very complex fields, like an earlier version of mu2E spectrometer, where there were actually solutions for particles that physically got trapped in the entire experiment unintentionally. Okay? Of course, in atomic physics, that's exactly what you want to do, but not physics experiments. Okay. Then multiple scattering, how does that come in? Right, so it distorts, of course, your angle measurement. You can work that through, and I'll simply give you the result in the end. Okay, so in terms of momentum resolution, right, we had this argument that it goes as L squared, then that it increases with momentum. You see that all here in this red line, which shows basically the resolution that you get from the point resolution of the measurement only. Now insert modest amount of material, 0.3% is actually quite small. Okay, just compute what that means in terms of a block of air. It's again one of those evening questions you can just do. Okay, you get something like this, and all of a sudden you see that at an EIC at a pseudo rapidity of 3 in a 3 Tesla magnetic field, which is pretty beefy, in the end, with 20 micrometer pixels of the dominant part of your area, your multiple scattering is a very significant contribution, and it puts an absolute floor on your performance at low momentum. So don't spend your time refining pixel algorithms at that point. Okay, spend your time thinning your detector. Acceptance edges, they matter as well, so be aware of them. You can read this at your leisure. Then in terms of Sagitta measurements, it's almost always advantageous to do that at the Sagitta point. So try to accomplish that where possible. For completeness, just performances as we currently know them out of EPIC. So what you see here is over a very large area, performances as necessary. You also see areas where they are above necessary. So that is one way of looking at this is it's a struggle to further optimize the instrument. But another way of looking at this is that indeed between the forward and backward region, you have a otherwise fully symmetric situation. What you're really bumping into are constraints on the compactness of the device that differ in these two directions. In practice, what that means is space for algorithms that use more than the tracking devices by themselves to still achieve the physics. Typically, these sort of requirements are single quantity determinations, right? So you do not consider calorimetric information, only track resolutions that you would need. By combining, you may work around and you may decide that that is better use, developing the algorithm is better use than further thinning your device. It's clearly what you're seeing here are these multiple scattering floors, right? Okay, displaced vertices, and there, since I think I'm running a slight amount over, let me just stop. There's no real summary here because this is a beginning in the end. Okay, I think most of us who are here because we like EIC, at least at this time. There are very good reasons for that, I believe. It's more than like. Now, the EPIC detector is well into its design. It certainly has a defined magnetic field, I would say at this point, which is probably the determining quantity for any experiment at the end of the day. It's typically not the thing that you upgrade. After a while, you might run it at a different field value, The magnet itself typically stays. So calorimeters are being call it prototyped, although in US project language, that's not always the right terminology. But basically, early test versions of them are being constructed, likewise for PID detectors as well as for trackers. I showed you these examples of MPGDs, which are forefront. I've shown you this example of the silicon sensors that are thinned to basically the thickness of a piece of paper, or about this amount of air, if you want to think in terms of radiation length. That's state of the art. So again, ample opportunities to engage with that at this point. For tracking as a whole, I think we've seen it, right? Even with something like quantifying the uncertainties on a linear fit that we all know how to do. Can get involved rather quickly, so just bite through. There's elegance in mathematics. There's elegance in solving things on a computer. Ample space to get involved. And with that, overall from this call, that I really hope that for many of you, this will be a start or an initial continuation. And certainly this call, I really value that it exists. Thanks again to the organizers. So thanks, Alexei and Fred in particular.
It was very, I mean, very good. One second.
Does this fringe field creates any problem for electronics and all? But there will be free fringe, right? A fringe field.
So you're absolutely right that in particular the size of the magnetic field is a concern if you would drive it higher for many of the optical detection devices. Okay, so, well, I mean, so for our PID detectors, we have in the end photon multiplier, although not the traditional version. I think your question about fringe fields may have come about from, let's say, having even Earth magnetic fields screwing up photon multipliers if you don't shield them. Right, so don't use the direct photon multipliers, but we do use photon detectors, and they are not capable of withstanding fields of, say, 4 Tesla, like used in CMS, which, yeah, call that chicken or egg, but CMS does not have particle identification capability. So the size of the field is actually the driving concern, more so than non-uniformities at the level we're currently dealing with. Okay, so you could not double the field, for example, without detrimental effects. You can go up to 2 Tesla in its nominal field. That I believe is safe at this point.
Okay.
Does that help? I think everybody's getting a head start on this evening's homework. Okay, thanks much.
Thanks a lot. Half an hour? Fantastic.